amplitudes. And in amplitudes, radial limit means large S, fixed T. And here S and T are the usual Mandelstam invariants. Okay? So why the Reggie theory, and why this Reggie idea? There is a general rule that people observe in experiments, that if you have some, let's say, two processes, one, something like this. Okay, let's keep. Let's say these are two S-channel processes. And let's consider these two cases. And this case allows for n particle exchanges in the T-channel. And this case allows for m particle exchanges in the T-channel. A general rule is that if n is larger than m, then the total cross-section of the n1 is larger than the total cross-section of the m1. Okay, this is observational fact. You see how it depends on the energy that you have on your lab, but you measure the total cross-section and you observe this fact. So it's a good idea to try to understand why this happens.
It's not very clear. What do you mean? Yeah, can you give some example? Which particles?
Actually, particle physics? I don't know.
Yeah, what does it mean?
No, but I can draw. People have done this. Like you have some energy in your lab, and they check how it depends on the energy, and they measure some process. The energy goes like this, and then
yeah,
it starts
but exactly
decaying,
not some process. Can you give example of a particular process so that we understand what n means and m means?
Well, okay, I don't know any specific example, but let's say in a given process, you allow for an isospin exchange 1/2, 3/2. In the other case, you only allow for isospin exchange of 1/2. Then this is n is equal to 2, and m is equal to 1. And I'm saying that this case, the cross-section is larger than this one. Okay? This is an observational fact. And people try to understand why this happens from the T-channel. So a good idea to study the T-channel is to use the partial wave decomposition of an amplitude, which you can write down like this. So A is the amplitude. I'm always considering scalars, identical scalars of mass m. I sum over the spin. Then there is some normalization. Okay, let's put just J. There is some partial wave coefficients, J, which depend on T, and then the Legendre polynomials of the first kind, which are functions of Zt, and Zt is basically cos theta t, where theta t is the scattering angle in the T channel, and these are related with S and T like this. Okay? So what we want to study is the radial limit, so large S and at fixed T. But this series converges nicely in the physical region in the T channel, which is T larger than 4m squared and S negative. So in principle, you should have problems with this series when you try to understand the radial limit. And you can see this from taking the large behavior, Z behavior of this. So when S is large, basically Z scales like S. And you can see that Legendre polynomial of Zt will scale like Zt to J. So if you have infinite number of particles, if you have to sum over all these coefficients, all these possibilities in the T channel, you see that this series will diverge, which is something you would expect. So the idea is the series is not a good representation. I should first write this down in some integral form, and then I start in the physical region. This converges nicely. I go to some integral form, and then I do the analytic continuation to large S. Okay, so this is the idea, and I'm not telling anything new. The idea is to consider complex spin and write down what is known as a Sommerfeld-Watson transform of this in this way. Then this, I'll say something. Okay, let's see, this is a minus here. And you can check this C is this contour. If you go to J-plane, the sine function has poles in all the integers. And you start with some contour C that goes like this. And you capture all these poles, and it's easy to check that if you capture all these poles, then you recover the series. Okay, so this is the integral representation we want, and this makes sense for any J, so this should also be some analytic function in spin. This is the claim, and a good one can actually write down an expression for these coefficients, which is given by the Frassager-Ribov formula. Okay, one claim before I write down the Frassager-Ribov formula, which is the usual claim, is that in the S plane, at fixed t, I'm only assuming that there are cuts associated with normal thresholds, which means this cut starts at 4m squared, and then there is the crossing symmetric one, u starting at u 4m squared. And you can also have bound states, but you can ignore them because you can observe what you mean by discontinuities and include also the bound states. So let's forget about those and just think that there are two cuts, one to the right, one to the left. And then you can write a J, the partial wave coefficients, in this way. So there is some integral over Z. Prime. It starts at some point in the cut, goes to infinity. Discontinuity in the S channel and discontinuity to the left, which I'll denote by disk in U. At fixed t, and this all comes multiplied by Alexander polynomial of the second type. And what I want to stress is that this factor exists. Okay? This is not a good thing, because what we want later on is to start with this configuration in the complex J-plane, and we want to open, because the Legendre polynomial scale is like this, the idea is that if there are any singularities in the J-plane, I should start with this configuration, open up the contour, and then close to the left, and pick the poles we want to pick. But to do so, as I open up the contour, I have to be able to drop the arcs at infinity. Okay? But because this factor exists, this can be plus or minus I pi j. So for large imaginary j, this will blow up. So this is not good. The solution is consider two contributions. One for even j gives you a plus. For negative j, for odd j, you get a minus. And if you consider these two, then you can drop these arcs at infinity. And these are the known even and odd signatures of the amplitude. Okay, it's also good to notice that this enjoys some symmetry. Okay, sorry. This is equal to -1 to the j. So you can actually split in only odd contributions and even spin contributions. And then you have, like, because I've erased the -1 to the j behavior here, I can drop these contours at infinity. I'm okay. And now, because I've dropped them, I can actually say something else from Carlson's theorem. These functions are unique. So I'm okay. I know that this actually means something. It won't change, like, because let me point out this out. If I start with some analytic continuation, I'm only imposing that this analytic continuation, when I go for integer spins, matches the partial wave coefficients that I had in the beginning. But then you say, if I have this analytic continuation, I add some sine function, it will also go to 0 at integers. So there can be many choices of a's, but because I'm imposing that it doesn't grow faster than this at infinity, in the right half plane, then Carlson's theorem guarantees me that this is actually unique. Okay. Okay. Let me. Okay. This is the usual story, and people split the amplitude in even and odd contributions. But there is another choice, which is related to this one, which are called the signature amplitudes, which I will write down now. So, okay, first, I will decompose the amplitude as a sum over some signatures, and this I'm calling signatures the deltas, which can be plus or minus. And then these are what I call the signature amplitudes. And these amplitudes only have either a cut on the right or a cut on the left. I remind you that the fact that I had to consider all these possibilities of plus and minus signatures came from the fact that I had a -1 to the j, and this -1 to the j came from the fact that I tried to write a single integral and putting the U channel cut on the S side. So if I only have right cuts or left cuts, then I'm okay. I don't have this -1 to the j, and everything should work fine. And this is what people do. And okay, these are basically defined like this. It's not really important, but where this function is, if you write down the dispersion relation for the amplitude, it means it's the right cut in S. This is the function that would have a left discontinuity in U, but I go for S, so it's only right-hand cut. So this only has right-hand cuts. And it's easy to check that if I have right-hand cuts here, I will have left-hand cuts here, and all of them will reproduce the full amplitude. And for people that know better the even and odd split, I can relate them. So minus. Where here I'm kind of abusing notation, and I'm writing U as minus S, which is true in the large S limit. Okay, so if I write down dispersion relations for A, I will have something. Okay, so S prime, 2 pi I, S minus S prime, some discontinuity in S, plus another term which is du prime, U prime minus U, disk in U. I'm saying that if I can write down a dispersion relation for an amplitude with only right-hand cuts, I call this RS T, and this is the dispersion relation for some amplitude AL of in U and T. But I don't write U here, I write S. Yeah, okay, I'm assuming that I don't need subtraction. That's important, of course. Okay, so now I started with some series representation of my amplitude. In a region where it converges, I went for a spinning representation. I have some coefficients which are unique and make sense at infinity. I can drop the arcs. And then when I move them, there can appear some poles, which are functions of t, that I have to capture. So I will open this contour, drop the arcs at infinity. This will come here. It will go like this, but I have to go around this pole and capture the pole. Pick the residue, sorry. Okay. I just want to say what people already know is that in the Reggie limit, large S fixed T, each of these signatures will have the expected behavior of, it will scale like minus S to some alpha T. There is some gamma for the poles in the sign. Beta T and I will mean, okay, this is because I have considered this function. As I vary the t, I can have some poles appearing in the J-plane. And this is what I mean by a regipole. This is at the location of the pole. And this bit appears here. There are, of course, other kinematical factors that I'm observing it in what I mean by beta here. And maybe something which is important to say is that these alphas, which are the Regge trajectories, in particular, I'm only considering the leading contribution, so I'm only picking the first pole. But they are actually a family of operators. So here, I said, if I go for large S, this series would diverge. But if I only have one contribution, let's say I only exchange some spin J, then this will go like some function of T S to some spin J. And this means that the total cross-section will scale like S J minus 1. And then you try to check, is this a single, is there a possibility that the single particle being exchanged in the T channel gives me the right behavior in S? And the answer is no. So what people observe is that if I have a spin 1, this would be constant. But this is not people observe. If it's a spin 2, it will grow like S to the linearly in S. But this is also not what happens. So it's some other behavior which is much smaller than 1 typically, and people want to reproduce this power. So what has to happen is that there should be some infinite number of operators that in some way they work collectively to reproduce this behavior. And in order to have that, these AJs should have some kind of delicate balance between them to reproduce the behavior. And that's why we expect that these AJs are in fact some analytic functions in J. Okay, this is more or less the idea. And this notion of a family of operators giving some behavior is what is restored when we consider the Regge trajectories as a regipole. Okay, let me go for 5 points. Okay. So for 5 points, the story is more complicated. I will put 5 here, and 3 and 4. There are several invariants that you can write down, but I will choose to write, I need 5 independent invariants. I will choose always 2 body type of energies, which I will call either Sij or Tij, depending if I'm expecting to take it large or not. And these are defined just like minus Ki plus Kj squared, where K's are the external momenta. Okay, these are incoming. And this then is S13, S25, S45, and these are the T12 and T34. So what is the limit that I want to study now is the so-called double Regge limit, where I take S to 5 and S45 to infinity. Necessarily S13 also goes to infinity. Tij's are fixed. And S13 over S45, S to 5, it's easy to check that if I scale this appropriately, then it can also be fixed. And this is what I call eta. Okay, this is my definition of a double Regge limit. And now I want to try to understand from the T-channel perspective what happens at large Sij's and fixed T. So I go back to the start, I write down some partial wave decomposition of this amplitude. And there are some new ingredients that make it different from the 4-point case. So there is a partial wave decomposition that goes as follows. There is some helicity, okay? Sum over spin J1, spin J2, that start at the helicity and go to infinity. Usually people can also write this the other way, right? Because helicity can go from, let's say you have a spin J representation, helicity can go from J up to minus J. But if I permute the summation in helicity and J, I can write this instead. Again, the normalization factor, Ji plus 1, this goes up to 2. Some partial wave coefficients, and then I have what are called the Wigner D functions, which are eigenfunctions of the rigid symmetric top, and basically they are also related with Jacobi polynomials. It's not so unexpected that things like this should appear. And then there is some other variables which we call Z, which are related with some angle, which I will explain what it is, called theta Toller, and this theta 1 and theta 2, I will also explain what they are. Okay, so what are then these angles? Let's look again for my amplitude. And let's lump together the particle 3 and 4. Then I can consider what is the rest frame of the exchange momentum Q1. And I say, in this frame, there is a notion of a scattering angle, which is what I call theta 1. Now I do the opposite, and I lump together 1 and 2, and I get some other angle, theta 2. Okay, maybe another drawing is better. Let me put like this. So I start with some process in a rest frame of a given exchange momenta. In this frame, P2 and P5 are in a common plane. I can choose some direction to be along P5. Let's call it Z. Then P2 is in some given plane. Let's say this is X. Okay, so P5 and P2 are in the same plane. And then there is another plane common to P3 and P5, which is the Q2 rest frame. This defines theta 2. And then there is an angle between the two rest frames. So I start, which is what I call the Toller angle. So I start with in a rest frame, I go for the other rest frame, and then I do some rotation from one rest frame to the other. And this is a new ingredient. This doesn't show up in 4 points, and we'll see why. The only scale Mandelstam type invariant that depends on this angle is S13. In particular, I can actually write down in terms of eta. It's nicer. It is some constant, not constant, it depends on t, but okay. Plus some constant now, and some function of t1, t2, t1, 2, t3, 4, and the mass, which is a polynomial of degree 2, but only eta depends on the Toller angle. And eta is related with S13, which you can actually see like in some way like a 3-body energy. And this is something that does not appear in 4 points, and this behavior is controlled by the helicity. So because before I didn't have that type of invariance, I didn't have to bother with the helicity, and I didn't have to bother with Toller angle also. Okay. So okay. Okay. So now I go back to what I said before, and I want to write this series as some integral representation. I start from the region where this converges, which is not at all clear, okay, let me say. There are very few results about analyticity of multi-particle production, and typically what they say is that if you do the analytic continuation in T12 and the taller angle, this is okay. If you do the analytic continuation, this converges nicely. If you do just T12 and taller angle, if you do T34 and taller angle, this is also okay. If you now have to also consider the other one, they don't actually know where this converges. So it's difficult, it's hard to prove that everything makes sense because you don't know exactly where to start doing the analytic continuation of your partial wave coefficients. So this is an open problem, also in amplitudes, as far as I know at least. But this has, I think people forgot about this after the 70s. And now I want to do the analytic continuation in spin, but if I do an analytic continuation in spin, then I also need to do the analytic continuation in the helicity. Okay, this seems more or less clear. But again, do I expect to have a good definition, a unique analytic continuation in these coefficients? And the answer is no, because I also have this type of problem as before. Let's say now that I assume that my amplitude in all the Sij's has this type of structure. So a right-hand cut and a left-hand cut. And now I want to avoid having both of them. So I either choose to go with the right-hand cut or the left-hand cut. And this introduces many more signatures, because now I have 3 types of S's, then I have 8 signatures that I have to consider. Okay, so I write my amplitude as a sum over all the possible signatures, plus and minus, and this will be something like S25, S45, eta, and the T's. Okay, yeah, I can forget about the T's. Plus, now I can go for the U cut, so I get the delta before. And I'm abusing notation and writing as minus S25, S45, and eta. And you see the game, right? Now I go for the 4-5Ks. Then I have the 2-5 and the 4-5. And eta, plus the delta 1-3, and I do everything again, but I send eta to minus eta. Okay. This gives me the 8 possible signatures, and the claim, even though it has not been proven, it only has been proven that it makes sense, again, because of the same thing, that if you do the analytic continuation in spin 1 and helicity, or spin 2 and helicity, this is okay, it's proven by White. If you try to do the analytic continuation in all of them, it's not proven, because you don't know where to start the analytic continuation. But the claim is that this should make sense. For each signature, I can do some kind of Sommerfeld-Watson transform, and it should be well defined. So, okay. There are some subtleties, because I am allowing for negative and positive integers values of helicity here, and because this is just Z, I have to separate the contributions from negative M, positive M, but later on I will only bother with positive type of, okay. The role in CFTs, the role of helicity will be played by what Petar called the Nij's, which are the labels for the tensor structures, and this can only be positive. It will go from 0 to minimum value of J1, J2. So all these problems of doing first the analytic continuation in positive M and then negative M, I don't need to bother about it, and I can just write something down. Do you have a question?
Yeah, so at some point you are still going to go to conformal Reggie theory, right?
Yeah.
This is just Reggie theory.
Yeah, I'm just this is Reggie theory for amplitudes. I'm just going along all the discussion, because then later on I want to try to generalize and say it's basically the same story.
Yeah. And then you just said that in the 70s, people started understanding these questions, and then they dropped it.
Yeah.
So what are the interesting, what's the motivation and the interesting problems? First, just in amplitudes, and if people dropped it even in amplitudes, why go to CFT and try to make it even more complicated? Do you have an example, say, in string theory? Do we understand what is happening in string theory?
In string theory, this works nice. You can write down a dual resonance model, and you expect some kind of Reggie behavior for that dual resonance model, and you check that whatever I'm going to write down next actually predicts the expected behavior in Reggie in string theory.
Yeah, what are the interesting, what are we trying to solve? What's the physics? What are we after? You said something in the beginning, A, B, C, D.
There are, of course, multi-particle amplitudes.
Yes.
A given limit that you can take is this double Reggie limit.
Okay.
And this will scale, you expect to scale something like S25 to some J, S45 to some J. I'm saying it's not exactly J, it's J minus M to 1, and 1, 3 to M. This is what you're going to see. You expect this for specific models. And then what I'm going to say is that you can get this behavior by studying all these signatures.
Yeah, it's just that it's getting a little bit technical. It would be better if from time to time you would help us with something a bit easier. It's a bit hard.
Okay.
Yeah, if you could tell, I mean, in string theory this works, and what do we learn, or what exactly
I don't
is
have
happening
here the
physically?
example, but if you write down the analog of Veneziano formula for 5 points in the integral representation, you take the Reggie limit inside that, you see that it gives the same answer that you would expect from this. So this seems to explain well what happens at the level Reggie limit in that case. So consider specific models. There are some subtleties in the proof that you don't know actually how to prove, but the end result, does it make sense? It seems to make sense compared to models. That's just the claim. In this case, you mean like CFTs? I think the mic is off, but the question was, can I prove that the amplitude is polynomially bounded? I will say something about it, and the answer is yes. Or you expect it is. If this goes through, then you expect that it's polynomially bounded. In CFTs, I don't know.
So could that be motivation for this work?
What, this?
Proving that the amplitude is polynomially bounded, could that be the motivation?
It can also be, yeah. But there are some technical steps. I want to explain now why we think that it scales like this, and this is some polynomial. This will actually scale like s to the j, 1, okay. Let's take lambda large. This will go like j1 plus j2. At most like this. Okay.
Can you make a few comments about more details on the analyticity you're assuming? I mean, what are you assuming in which domain, and what is a guess, and what is solid?
You're saying this? I'm just assuming this, that the same type of analyticity properties of 4 points for ds it's also true for all the SIJs.
So, to be more precise, here you're in the physical domain in L variables, and then you're analytically continuing on a subenergy with everything else fixed. I mean, what does it mean, everything else fixed, since you have kinematical constraints?
No, it's a difficult question, yes. But this is the assumption. If you want, the assumption is write down some dispersion relation for your amplitude, which makes sense if you assume that this is the structure for all the SIJs. And this is an assumption. Nothing has been proven there, I guess.
Sorry, I'm a bit confused. Don't we know this assumption is wrong, that as soon as we have more than 5 particles, we have anomalous thresholds, and even if you just scatter 1 particle of mass m, don't we know there are many more cuts beyond these ones?
But that discussion comes in 4 points also, right?
No, if you scatter
No,
4 points,
I'm
if you
saying
scatter
that
the
at some
lightest
point you should
particle,
have
there are only these cuts. But if you scatter 1, 1 goes to 1, 2, where 2 is a heavier particle, then yes, you can start getting anomalous thresholds. But when you have 5 particles,
Yes.
because 2 particles can always fuse, right, into a heavy guy, you always have anomalous thresholds. And I thought 5-point amplitudes always have many more cuts than this, but
I don't know.
so this is never true, I think.
Okay, let's say that in CFT it doesn't matter. Okay, so I'm interested in CFTs. I will assume that this is, you can also work with these ideas. For amplitudes, I don't know. But this is the assumption, that this is the cut structure. You might say it's wrong, but it works in models. So you have to understand why.
But does it work because it's 3-level string theory, or does it work on models where you have particle production?
Yeah, that's a good question.
It's
Probably because
if it's 3-level, then you don't even have cuts, right?
No, that's true. No,
maybe
it
in this
depends
high
on-
energy limit, these other cuts that I'm mentioning, these anomalous thresholds, maybe they are irrelevant, but that's possible, that perhaps those cuts don't matter, but...
Can be, okay, yeah. I'm not sure, but this is the statement they have. I can say more than what is the analytic properties of in any Sij for multiparticle amplitudes. I don't know what it is. I don't think anyone knows exactly. They, I'm saying Weiss, White, Goddard, people from the 70s studying these things. Okay, but if you're not happy with this, let's move faster. So this is what you would expect. If you assume that's true, you do the Sommerfeld-Watson transform, and in the end, you can just write down something like this. There is some contour C. There's also a contour in J. So this should also CIs. 2 pi I. Okay, I can absorb this. And I will just write the singular behavior that we should comment. Okay. So the claim is assume that, then you write down some Sommerfeld-Watson transform, you absorb non-singular factors in what you mean by A, and this is a good, it makes sense as an analytic continuation in all of those numbers. Much time okay. Let me just comment on the poles. So, as before, I'm allowing for poles. Okay. In these A's, in J, the important claim is that I don't allow for dynamical poles in M. So this is a sum function, sorry, M and Tij's. You'll have some poles, and I'm studying double Reggie, so I have 2 poles. And then this function is a function of the T's and M, but is regular in M. Okay, so if I have the the actually J and M planes. I have the usual poles in J. I open up the contour and I pick this pole. This is Ji or alpha I. Okay. Now, if I do first the integration in J, I'm highlighting these two types of poles. So there are poles here, which correspond to the gamma minus M. And I'm moving the poles up so they don't overlap in this drawing. But this comes from the Ji plus M. What I'm saying is that no extra dynamical poles in M. Why is that? The reasoning is bifolded. One of them is due to a Barbanel, and you can also use it in CFTs. The other one uses Steinman relations, which we don't know what it means in CFTs. So a Barbanel statement is that because this is, okay, I didn't write this, it's here. Because if I allow for poles in M, in particular the Regge limit would have some asymptotics which is determined by M, and M is not a good Lorentz invariant number. So if I do some Lorentz transformation, M can change. So I'm expecting that the behavior can only depend on things which actually label particles. That's the whole story, right? In the T channel, I have some particles being exchanged, and this determines what is the S behavior in the large S limit. So it should, in principle, be some label appearing. The asymptotics in large Sij should be determined by labels of the particles itself. So either mass or spin, no helicity. This is the statement by Barbanel. Steinman relations say the following. Let's consider some amplitude. You have some Sijs as the Steinman relation said this. If you have some, in this case, it's like this. Discontinuity in S25 and discontinuity in S45 of the amplitude should be 0. And the statement is more general. Is if you have any partial overlap of the external momenta in your definition of the Mandelstam invariance, then the successive discontinuity should be 0 in the physical regions. So you come here and you say, if I allow for poles in M, or some dynamical singularity in M, then S25 and S45 can both contribute to with a branch cut. So I would have some non-vanishing discontinuity in S25 and S45, and this is forbidden. So M should be some equal to J minus some non-negative integer, such that I don't have this problem. And these are exactly the poles that I've shown here. So these are the poles I care about, and there are no extra singularities in M.
Naive question. So first of all, the only model where you can test everything that you are saying is three-level string theory, right? There's nothing else where you can test any.
I've seen people, okay, if you take the Regge limit of any, like consider n equals 4, people have done this. They consider taking Regge limit in n equals 4, and they see that the scaling is this one, the S25 to the J, S45 to the J, eta to some power which is determined by J again. It's not.
Regge limit of what in n equals 4?
Just do some multi-particle computation.
What particles? What particle?
I don't know exactly, but they have done this. You can see, like people consider some amplitude in n equals 4.
But there are many amplitudes, right? You can scatter many things in n equals 4. What exactly?
Exactly, I don't know.
It's in the planar limit?
Yeah, I think so, right?
So it's also, again, some three-level string theory.
Yes.
Okay, so it's always three-level string theory where you can test these things, right?
The examples I know, yes.
Okay. So it's okay to think that we are exploring like the space of three-level string theories probably when we are doing this discussion.
Probably, I'm not super sure of that statement, but I would say so. It seems.
And then just a very
reasonable.
naive question, that's probably silly, but since strings are not exactly point-like and these Steinman relations are very much derived for field theories, could there be any kind of subtlety that you could have some discontinuity provided it's very small and so on? Because Or am I just being silly?
I don't know if, I think this is a generic statement for any QFT in which you can define these S's. It should be always work. There are some subtleties which maybe you can think about, is like, if you are outside the physical region, then this doesn't have to be true. So if you say, for some reason, this asymptotic behavior is achieved outside the physical region, then this is not true. And you can have like some dependence on M and dynamical poles in M. I'm just saying, if it's a physical region and this is the asymptotics, then M shouldn't have any dynamical poles. Okay, but let's move to actual CFTs, finally. Okay, and I will start with the 4-point. Let's consider the usual Regge limit in 4 points. You start from Euclidean configuration, and then you do the analytic continuation to Lorentzian correlator, which is in the order that is compatible. Sorry, let's do it like this. So this is 4, this is 1, this is 2, and this is 3. So 2 is in the future of 3, and 4 is in the future of 1. Okay, and I'm considering a Whiteman function in this order. And what is nice about this, or what we think it's important when you try to generalize this, is that the behavior in OPE in the cross ratios is that both of them go to 0, but you have crossed cuts. Okay, so you can actually check if you have some block. You consider the analytic continuation from Euclidean to Lorentzian. You do the usual epsilon prescription. Ti, you do the analytic continuation for any Ti you want, and then you take epsilon I to 0, but you keep the order. Okay, and what you get is that if you look at your block, or let's say you look for what happens in one of the cross ratios, let's say Z bar, there is some cut in the block starting from 1, and you see that Z bar starts somewhere, and then you cross the cut, and then it goes to 0. And Z you can keep fixed if you want during this. And the block, you'll see, as it goes through the cut, it will develop, let's say, delta and J. It will capture some monodromy. And the role of J and delta will be permuted. And this is the leading contribution in the Regge limit. So in 5 points, what we want to, if you want to generalize the Regge kinematics to 5 points, what we are looking for is define some kinematics which matches, in terms of the cross ratios, the OPE, the Euclidean OPE in 1, 2, 3, 4 channel, but you have crossed cuts. And you can actually check that these cuts are crossed. Okay. And our proposal, which is not unique, okay, is the following. Now you start with 5 points. You cannot put all the points in a single plane with conformal transformations. So you start in some Euclidean configuration at time t equals 0, but you have some point 5, which is outside, which has an extra dimension. But I'm putting a circle around it to say that this point has some height. And then you do the same as in 4 points. You move 2 here, 3 here, 1, 4 here, and 1 here. Okay, so the causality relations are 4 in the future of 1, 2 in the future of 5, which is in the future of 3. Then you can check, is this a good prescription? You look for your cross ratios. I'm using the following cross ratios. So this, sorry, I should use this. This is x12, x35, x13, x25. And then all the other ones are defined from this one by cyclicity. So this is equal to ui plus 1 is equal to ui, where you say that xi goes to xi plus 1. And what happens in the Euclidean limit is that u1 goes to 0, u3 goes to 0, u2 goes to 1 plus something that scales like epsilon square, where epsilon is small. 4 also goes to 1 with epsilon, and 5 also goes to 1 with epsilon. Okay, and you can check. Consider this time ordering, so 4 in the future of 1, 2 in the future of 5, and 3. Do the usual prescription, see what happens to your cross ratios, and you see exactly that this, for this kinematics, this is true. Okay, now, have I crossed cuts? Yes, because I crossed light cone singularities between the operators, I can actually believe that there are some cuts. But if you want to actually check, we have integral representation for light cone blocks of 5 points, and these blocks have they have branch cuts when in UIs, starting from 0 to U2, U4, and U5. They have discontinuities in these 3 variables, starting from 0 to minus infinity, or you put it somewhere else, but you can actually check that these cross ratios will do the following. So U4 and U5 go this way, and U2 goes the other way. So they actually cross cut. So you pick some monodromies, and you've defined something which makes sense in terms also of Euclidean OPE. It scales in the same way.
Sorry.
Another thing that is important, in 4 points, you can just use a single rapidity gap.
Sorry, is your configuration really analogous to what you were discussing in amplitudes before? It seems like you have less boosted things.
If you want, send this operator also to infinity, boost them, it's also fine. As long as you keep this, it's also fine. If you want 3 operators to going like being boosted in relation to each other, this is also fine. We just prefer to have a fixed point fixed. It's easier.
I also had a question. So in the example for the 4 points, we know that in this configuration, using the T-channel, we can show that the 4-point function is actually finite and smooth. Here, is there any convergent to P channel for this configuration that allows you to control this 5-point function?
Okay, yeah. In principle, it should not converge, right, the OPE?
No, but there are various OPEs, like the S-channel OPE there also did not converge in that limit that you're considering on the left. But there's a T-channel OPE that tells you that the thing is okay. Here, is there some OPE where you're not crossing any cuts?
No, we have no proof of that. We are just assuming that it should be possible to check that that's the case, that you can bound in some way this Regge kinematics by some Euclidean kinematics, but we don't have any proof of that. Usually the proof follows from Rindler positivity, right? And in this case, you need some symmetric configuration.
No, there is no Rindler positivity. On the left, it's a trivial thing. It's much more trivial.
If it's identical scalars, yes.
Identical, non-identical. You use some Cauchy-Riemann.
Okay.
Here, Cauchy-Schwarz. So here, what's the reason you say you expect that it's finite? But what do you expect? Based on what physical reason?
Seems to make sense that if you follow the good I epsilon prescription, this should converge, but we don't have any proof.
I mean, it doesn't have to converge. Maybe something is a distribution, there are correlation
functions. I'm saying it should converge at least as a distribution. That would be the statement.
I see. Okay.
And you can actually try to prove it, but we don't know exactly how to prove that statement.
It's okay not to prove it, but at least not to make some statements that don't follow from anywhere.
Yeah, I'm not saying that these OPE converge. I'm just saying that the cross ratios look like the Euclidean OPE between 1, 2, and 3, 4, which has the usual interpretation that you can pick this operator 1, move it to the next Poincaré patch, and you'll see that 1, 2 are approaching each other. And this also works here, but we don't, and because of that, the cross ratios look like this, but we are not saying that the DOP actually converges or anything. Okay. What do I need to say next? Okay. So we have discontinuities. How much time do I have? 15? More. Okay. 20. Okay. So we have discontinuities to take, and because of that, we go to Mellin space. Discontinuities in Mellin space are trivial. You just get a phase in your cross ratios. The structure is also easier in Mellin space than the higher point conformal blocks in position space. And because of that, we went to Mellin space. But let's just relate it with the position space ones. You have some, okay. I can define some Mellin variables, Tij, Sij, which basically will have some good, oh sorry, it's not that. We'll have some good an analog with the flat space case. I don't think I need to write all. But let's write it anyway. U5. There is our Mellin amplitude, which depends on Tij's and Sij's. As you go for the Regge kinematics, you pick some phase in your cross ratios. Times the products of several gamma functions, and while this might look that it was going to diverge for large S's, imaginary S's, actually the gamma functions will cancel that divergent behavior. But what is important to comment is that if you take this limit, or in particular if you, let's say that U1 goes to 0 like sigma, U3 goes to 0 like sigma 2, and all these things will go like, this is a plus or minus, depends on my definition, it's not important. Okay, sigma 1, sigma 2, some angle which is fixed, some angle which is fixed, as I take sigma to go to 0, and I take this behavior, I can see that this analytically continued correlator, the dominating part of this integral is given by considering S13 going to 1 over x squared, S25 going and S45 as 1 over x, where x goes to 0. So this is exactly the type of expectation that we have for double Regge limit, and this seems to tell us that this is actually a good definition of Regge kinematics. One more thing that you can check is that Casimir equations are solved if you assume the following scaling in S's. Okay, this L runs from 0 to minimum of J1 plus and J2. But it's not exactly the same L as before. It's a different choice of basis. But let's say if you have this behavior in S and some function of T1, 2, and 3, 4, then this can satisfy the Casimir equations. You get some equation for F, but this is fine. And if you have this behavior, then as you do this integral, you'll see that actually your block will scale like something like sigma 1, 1 minus J1, sigma 2, 1 minus J2, times some function of the angles. And this is what we would expect for a good definition of a double Regge limit. Okay. Now, what is actually needed for doing Reggie theory? Again, we'll do the partial wave expansion for a CFT in the principal series, but we are considering Mellin space, and this can be written by just doing the inverse Mellin transform from definition of the partial wave to Mellin space. I'm also assuming principal series representations. There is some coefficients which depend on UIs. And here we have what we call the Mellin partial wave. So it's the inverse Mellin transform of the partial wave itself. And because this also solves the Casimir equation, it should also have this type of behavior. What is relevant is that as you close the contour in nu, this goes from minus infinity to plus infinity to the lower half plane, and you pick, you should reproduce from this thing the usual OP expansion in terms of conformal blocks. So this imposes that these coefficients should have poles in nu, and here we should have the product of OP coefficients relevant, and there are some factors here which are related with shadow coefficients. And let me stress that these things related with shadow coefficients are only known in terms of some finite sums, shadow coefficients, but no closed form expression for them is known. This will involve shadow coefficients of 2 spinning fields and 1 scalar. And if you want to do all this story, you should actually know this in some closed form that you can do a analytic continuation in spin. We don't know them. We are assuming that this should exist in a nice way. Okay, so this is the behavior in B's. And as you close the contour in nu, you pick these poles and you get the OP coefficients. And if you go for position space, you'll get the block here, and everything works fine. Now, I want to know what these functions are. Okay, these are the inverse Mellin transform of the partial wave in position space. But in general, if you want to know some closed form expression for these, it's very hard. Otherwise, you will have solved all the problem. But one case that you can actually compute is the one where the exchange particles are just scalars. And you can check by doing the usual computations from partial wave or in Witten diagrams. You can check that you get that this Mellin partial wave will be just a sum of 3 F2s. Doesn't matter what is here, evaluated at 1. And of course, this is only a function of T1, 2, and T3, 4. Okay, so this is the case that we can actually compute in some nice closed form expression, even though it doesn't look that nice. But these partial waves, in general, these partial waves also solve this. If we impose that this is the behavior, they should also solve the Casimir equations, and this imposes some conditions on F, which is the following. Sorry. Okay, F. Okay, we have some equation for this f, where this f a1, a2 is basically the original f, where I shift t12 by a1 and t34 by a2. One nice thing of this equation is that if you want to, because we know the scalar case, there is some symmetry to get this equation for generic spin, for the spinning case. Okay, let me be precise. If J1 is equal to J2 for generic L, you can get this equation from the scalar version if you do the following shifts. So where is it? So at least for these cases where the spins are equal, we can get the Mellin partial wave for this spinning case from the partial wave for the scalar case. For generic spins, we don't know how to do it in a nice form. Okay, but let me push.
Yeah, so I thought I'm a bit confused. This 0, 0, 0, is it a parenthesis? Because I thought we cared about complex spin and generic spin. Is this 0, 0, 0 just
I'm saying
a statement that you understood something about conformal blocks?
Yeah, I'm saying this is a
5
generic
points?
statement about the partial wave even away from the...
Yeah, so this has nothing to do with
The
Reggie
radio
theory. It's a
limit. I'm just saying
parenthesis
that we
just
need
saying
this-
if the spins are 0, you also have an
Yeah.
expression for the conformal block.
Exactly, basically.
And then you are saying that,
I'm saying
and if
that-
the spin is not 0, but if they are equal, I can
can
now
do so.
use this result to also find it, but your hope is then to compute many, many spins to guess the analytic formula that you need.
Yeah, that would be the case. This case clearly gives some analytic formula in this specific case of J1 equal to J2 for the Mellin partial wave that you can after do the analytic continuation. You can do the Sommerfeld-Watson transform in this. Okay. If you don't have this expression, then you're doing something and you are assuming that you can write some closed form expression for that.
Okay, I'm afraid that you will end up in the talk in the middle of writing some sharp but not super illuminating formulas. Make sure that you have some time for general conclusion.
Yeah, okay. I will just write down the final claim. So let me go back a little and try to make this clear. So as in the flat space, we start from the partial wave decomposition. Now we want to do some Sommerfeld-Watson transform to write that in terms of an integral representation. We need to know what these functions are, and these functions, if the spin J1 and J2 is the same, for generic L, you can get it from the Mellin partial wave that we know for the scalar case by doing these shifts. If that's not the case, we don't know the closed form expression for that. You can write it down as like 30 sums, which depend on spin, which is not a good thing to do analytic continuation with. But let's assume that you can actually do that you can actually find some closed form expression for that. What is the good Reggie theory in Mellin space? So we have, okay, I should have erased this one maybe. So we have this behavior. Now we want to do the analytic continuation, but is this a good function to do the analytic continuation in both J1, J2, and L? And the claim is not, okay? That it's not. Again, as in the flat space, you need to consider 8 types of signatures, even though to actually make a good statement about that, you need a closed form expression for this. I will remind you what happens in 4 points. In 4 points, your Mellin partial wave enjoys the symmetry, this symmetry. So, and again, I find some -1 to the J behavior, which imposes me that, in principle, this is not a good function to do an analytic continuation with. So what I can do next, in 5 points, I don't know how to prove this statement. One thing that I know is that at large S, they'll scale like S to 5 to some power J1 minus M, 4, 5 to some power J2 minus L, sorry, I'm using L here, S13 to the L. So if I take this with a minus, then I get some symmetry that if I, okay, if I send S25 to minus S25, I get some S25 minus 1 to the J prime, S25 J1 minus L, where J1 prime is J1 minus L. And what I'm saying is that you need to actually consider 8 signatures. Let's say the signature is called by theta. Okay. And I should actually consider eta here. And all the signatures are defined as before. So 2, 5. Okay. Can put 1/8 here. Okay, what I'm saying is that you should sum over all these possible signatures where the signatures are defined as before. When you send S25 to minus S25, you get a minus 1 to the J generically. We can only prove this statement for the large S behavior because otherwise we would need to know the full expression for the Mellin partial waves. In conclusion, okay, as you start in M-plane, you can do the Sommerfeld-Watson transform. You pick these poles. There are other poles right here. In the J-plane, you have some Reggie poles, which are basically the J's that satisfy the equation that I wrote before. So whenever this is 0, we should have a pole in Ji's. So it should be here. So I start from the given some Sommerfeld-Watson transform. I start here. I open up the contour and I pick this pole. And what you get in the end is that your Mellin signatures, the signature amplitudes in Mellin space.
You are more or less out of time, João. So
Yeah, I'm just
I don't
writing
know
the
how many
last
formulas
equation.
you want to write, yeah.
I'm just writing the last equation. You pick the poles in L, so in J, sorry, S45, J2 and U2, and then you have the integral in L to take all these coefficients. Also need to have some signature. The f function that I had before also appears here. And I have some behavior in eta. And I have the remaining poles that I have to capture are basically determined by J as before. So I have some Ji, eta, nu I minus L. This is the behavior. So I've captured the poles in J. I have some Mellin representation in the principal series. These are the behavior in S. Then I'm left with taking the poles in L. And now the argument is that there are no extra poles other than this by using the same argument as a Barbanel, that L here is just a label for the choice of basis of 3-point function, so it shouldn't control the symptotic behavior. So the poles that I need to care about are these ones. So these poles here and the poles also in Ji minus L. Okay, one thing that happens in the flat space is that the actual definition of the partial wave will cancel poles. So there are poles from here. There are poles in minus Ji plus L and poles 1 plus Ji plus L. And the actual partial wave in that case cancels these poles. In here, we don't know exactly what happens because to do such a statement, we need to know what is the full expression for the melon partially, but in principle, if that happens, you only need to care with some poles that are right here. And you capture all these. We don't know if that's true or not, so let's just say that there is some contour like this, and then as you move to the left, if you want to take eta large and you close the contour to the left, you should pick the poles, and the poles are completely determined by the complex spin poles. And I'm sorry for going over time a little bit.
Okay. Thank you. Any question? If not, before we thank João, I forgot one small thing. When we go to the buffet place, there are two options. You can either go through Paulista or through the bridge. There is a crazy person on the bridge normally, but the person is always on the right side of the bridge. So just walk on the left, and then it's okay. I mean, the crazy person in person is harmless, but sometimes not. But 99% yes.